Hello friends, welcome back to the channel. If you like this video, please like, share, subscribe. I'll share this video's command to my experts. Without wasting a single minute, for latest update, hit the bell icon. Let's begin to our today's topic. Let's begin.
Google has officially released HEIR, an open-source compiler toolchain that allows AI models to process encrypted data without ever decrypting it. Normally, a server must temporarily decrypt incoming user data to run its calculations, exposing that data to potential network breaches. With HEIR, the input data remains mathematically locked as ciphertext. The server runs inference and returns encrypted results without ever seeing the underlying data. Bypassing the decryption step entirely removes the primary security vulnerability of cloud-based AI processing. Implementing homomorphic encryption historically required dedicated teams of specialized cryptographers to handwrite and configure the complex mathematics. This architectural diagram details how HEIR removes that dependency. It relies on a multi-level intermediate representation, or MLIR layer, to automatically translate standard developer code directly to specialized hardware protocols. This automation converts niche cryptographic theory into a deployable tool accessible to general software developers. To measure practical viability, Google tested 4 specific enterprise applications compiled with HEIR, all running successfully on a single-threaded CPU. The first application is content recommendation, delivering personalized user suggestions without tracking or compiling underlying profiles. Second is fraud detection. Banks can accurately flag suspicious credit card usage while maintaining total financial data privacy. The third and fourth address security protocols, intrusion detection for scanning encrypted network packets, and hot word detection to process audio wake words without recording plaintext speech. These validations prove that highly regulated industries, like finance and cybersecurity, can execute predictive analytics without exposing their strict data silos. Slight pause. Computing over encrypted data inherently demands significantly higher processing power than standard plaintext inference. This animation compares compiler logic. Rather than translating code sequentially, line by line, AIR uses structural rewriting to optimize the entire computational layout of AI operators in parallel, minimizing total processing latency. To further offset the computational load, Google established partnerships with hardware accelerator firms like Belfort, Niobium, Kornami, and Optilisys, while releasing the Jaxite cryptography library for specific hardware integration. Enterprise development teams can evaluate specific AI models and hardware setups directly by accessing the source code on the Google Fully Homomorphic Encryption GitHub repository. With automated compilation and dedicated hardware scaling, Fully Homomorphic Encryption has moved from academic theory into a structural, accessible enterprise reality. In this representation of a standard AI inference process, we see the core vulnerability of modern computing. To analyze a query or run an algorithm, conventional AI models require raw, plain text data. Even if encrypted in transit, it must be decrypted on the server side to process the information. That momentary exposure creates a massive liability. If a cloud server is processing sensitive medical records or financial transactions, having information exist in plain text on the server exposes user data to internal breaches or cyberattacks. This diagram illustrates homomorphic encryption, or FHE. FHE allows computational math to run on an encrypted input, a ciphertext, passing through the algorithm without conversion to plaintext. Because the server infers directly on the ciphertext, it returns an encrypted result only the user can decrypt. FHE solves the server-side privacy problem in theory. But historically, deploying this math in real-world scenarios has been blocked by severe operational barriers. 2 main bottlenecks prevent wide-scale adoption. Processing ciphertext demands enormous computational power, resulting in high latency, and implementing the cryptography requires a highly specialized skill set. Adapting a standard pre-trained machine learning model to homomorphic encryption usually requires a dedicated team of cryptographers. They have to manually rewrite the model's codebase to accommodate the complex math. To remove that manual bottleneck, Google developed HEIR, the Homomorphic Encryption Intermediate Representation. It is an open-source compiler toolchain designed specifically to automate the translation process. HEIR functions as a bridge. It sits between general software developers building standard AI applications and the specialized, mathematically dense environments required for FHE. By automatically translating and optimizing pre-trained models for encrypted inference, HEIR aims to eliminate the need for bespoke cryptographic coding in the software development lifecycle. To understand how HEIR achieves this automation, we can look at the role LLVM plays in traditional software programming. Traditional compilers act as universal translators. They allow a software developer to write code in one language, and the compiler automatically converts it into the specific machine code required by different CPU architectures. HEIR applies that same architectural logic to cryptography. It prevents developers from having to hand-write complex cryptographic instructions for every unique AI model they want to deploy. This map shows the compiler structure. MLIR acts as the central hub between standard AI models above and FHE encryption styles below. When an unencrypted model enters, the MLIR layer converts the code into a neutral state, then routes it to the required cryptographic scheme. This intermediate structural layer allows the toolchain to process standard inputs into FHE-compatible formats without manual line-by-line translation. Bypassing the cryptographer solves the expertise problem, but processing encrypted ciphertexts inherently requires far more computational overhead than processing plaintext data. If a compiler simply translated an unencrypted AI model into FHE code line by line, the resulting program would execute sequentially, resulting in inference times that are prohibitively slow. To address this latency, HEIR utilizes a specific optimization mechanism within the MLIR layer, known as structural rewriting. In this graph, standard AI operators function in a linear chain, where each step must complete before the next begins. Instead of direct translation, structural rewriting dismantles this chain. The compiler reorganizes the entire layout into a densely stacked parallel matrix. By optimizing the spatial layout of the math itself, the compiler enables the hardware to process multiple encrypted operations simultaneously, reducing total processing time. This structural rewriting is the core mechanism that brings FHE latency down to levels that are mathematically viable for production-scale models. To demonstrate the efficiency of this structural rewriting, Google compiled 4 benchmark applications through HEIR, running them on a standard single-threaded CPU. The first benchmark demonstrated content recommendations. The HEIR compiled model delivered personalized suggestions without tracking identifiable user profiles. The second application, fraud detection, flagged suspicious credit card usage while keeping the financial data completely encrypted. Third was intrusion detection. The compiler analyzed encrypted network packets to identify security threats, all without decrypting. The system identifies anomalous network traffic and isolates malicious packets in real time, strictly preserving the integrity of the surrounding secure data. Finally, the hot word detection benchmark processed incoming audio to listen for specific wake words, executing the inference without recording or storing plaintext speech. Executing these 4 distinct inference tasks on a basic, unaccelerated CPU proves the mechanical efficiency of HEIR's structural rewriting. Software optimization has physical limits. Running large-scale commercial AI models requires more compute power than a single-threaded CPU can provide. To push massive ciphertext processing to an enterprise scale, the software ecosystem must integrate with specialized FHE hardware accelerators. To bridge that gap, Google released a software library alongside HEIR called Jaxite. This pipeline illustrates Jaxite's role as an interface layer. It takes structurally rewritten models from HEIR and passes them to physical accelerator arrays like GPUs and TPUs. To supply this hardware, Google partnered with accelerator firms like Belfort, Niobium, Kornami, and Optilisys. The ecosystem is further refined through academic collaboration, with researchers from institutions like Carnegie Mellon and Georgia Tech optimizing the integration between the software and the physical accelerators. The structural rewriting performed by HEIR at the software level, combined with Jaxite's integration into physical hardware arrays, creates a comprehensive pipeline for minimizing ciphertext latency. The entire toolchain is designed to operate as an integrated pipeline. The workflow begins when a developer inputs a standard, unencrypted machine learning model into the compiler. Immediately, HEIR takes over. Through the MLIR layer, it analyzes the code and automatically rewrites the structural layout to optimize it for encrypted math. In the final deployment phase, That optimized model routes through Jaxite directly to the chosen hardware accelerator, ready to receive encrypted inputs. The data transitions into an impenetrable format, mathematically secured against external exposure, while remaining fully functional for the model's algorithms. By abstracting the complex cryptography away from the software developer, this automated pipeline allows for the direct deployment of secure AI inference from standard model formats. Private AI was previously confined to academic research and specialized cryptographers. Now, the tools to build it are centralized in an accessible ecosystem. By releasing HEIR as an open-source toolchain, general software developers can now build and deploy FHE-compatible applications without needing specialized training in advanced cryptography. The security guarantees established by this ecosystem are purely cryptographic. They rely entirely on proven math, rather than trusting the security protocols of specific hardware vendors. For cloud architecture, the implications are precise. Server platforms can now process highly sensitive user data and execute complex algorithms without assuming the liability of storing that data in plaintext. By providing an automated path from standard ML formats to hardware-accelerated FHE, FHE-IR establishes the technical infrastructure required for cryptographically secure AI to function within modern production environments.